All right, day 3. We're gonna continue on with these lectures. We're gonna just pull up. Where in the world? Maybe pull up my GitHub repo that contains all this. How's everyone doing today? I hope everyone's doing well. There we go. Last and cryptography. All right. So we're still on lecture. There we go. We're still on lecture 2. Oh, sorry, lecture 1. We'll probably be doing this for like an hour and a half, probably. So let's just recap. Get some music going as well. And let's just lock in here. I uploaded the video right now. I'm gonna shower after this. Okay, let's go. Let's close these tabs. Okay. Okay, cryptography and C. Okay, so we left off yesterday on the determinants. Right here. We left off after. Oh my goodness. Sorry. All right. We left off after 2.11. So let's look at 2.3. Minimum distance. So 2.3 states. Okay. Yeah, I've been stacking in comp arc recently just because I don't know, it's just not interesting right now. We're doing assembly code. It's not that interesting and all that. So that's why I'm doing this. I love this more than I love the other one. Anywho, minimum distance. So let's write this down because oh my gosh, please iPad stop tweaking. Bro, my iPad is tweaking out right now. Bro, what in the world? Bro, what is going on? Sorry about that. My things are tripping out right now. There we go. Okay, it has a non-sequence V. That's space of minimum length. Under some specified oh my gosh. Okay, so I'm trying to understand this. This is, I think, less trivial to understand. This is kind of a hard definition. This is more abstract because I'm not sure what a Euclidean norm is. This element. That makes sense. So the short answer for this, or the short interpretation for this, is just that there is some. So what we're gonna do right now, we're gonna look at what a Euclidean that is. Euclidean norm. So this is the first time I'm gonna do this. We're gonna pause the music and we're gonna look up what a Euclidean norm is. Okay. Let's live stream this. Let's Euclidean norm is. All right.
In this video, let's learn the Euclidean norm of any vector. This is the Euclidean norm of the vector e. See that on purpose I didn't write e in the bold form, because in some books the author write in bold, in other books not. And you must have the mental flexibility to understand the concept rather than memorize a specific notation. What we do here is square e1, e2, and the en, and then take the square root. Let's import numpy as NP and define the vector e, numpy array, minus
Okay.
3, 2,
Cool.
the normal en.
Oh, okay. So it's way easier than I thought. It's way easier than I thought it was going to be. Essentially, just means you just square it. You add each of the squared terms and then you square it the sum of that. So, I guess a better question now is why does that matter? I think this relates to. I just can't remember what the. I just can't recall. So let's just look at what the norm even is. Euclidean norm, which we just make sure, right, is just norm. The norm is a function from a real commute with scaling. Oh, I remember doing this now. I see. I think this is, we're gonna once again check out the forbidden fruits of ChatGPT to give us some examples and hopefully just. Okay, let's go ahead and just understand this a little bit more. Talk to me about the Euclidean norm and why it's important for lattices. Let's get a more concrete definition. Right, which we already know how it's calculated. We're not worried about that. So it's important to the SVP, but not why. Why is it important? Right, we already know the lattice definition. Just why is it important in general? I mean, that's cool that it's useful for what we're trying to do, but before I do that, I want to understand why it's even important in the first place. I remember the error norm. Yeah, there's the error norm. I can't tell you exactly. It's not really helping me out. It's not helping me out very much. Let's go back to Wikipedia. It doesn't help out too much. I guess, yeah, I guess we can just call it the magnitude. I heard this term last semester. If I'm not mistaken, this just means when you take a vector, you normalize it. All that means is you take the vector and you put it in respect to the space So it scales properly. And I want to say norm, and it has to do with orthogonality. So I know it's important. We'll get to it later because I'm sure we'll have to do it later on. Anywho, okay, definition. 2.13. Min the min distance of L is I'm just trying to. Is that an eigenvalue? So the eigenvalue of L. So same with the walrus operator. Here we go again. Equals min V spans L. Oh, hold on, my handwriting is messy. It's messing me up here. In the meantime, we can try to understand this a little bit more. Okay, which is also equal to min distinct x and y in L, norm of x minus y. And it says here that this says recall x minus y. I want to first talk about why this x minus y is a non-zero lattice vector, because that, once again, that doesn't seem very intuitive. So I want to draw that out a little bit here. So let's just take a look at this closer and see. So non-zero lattice vector. If I have a lattice, even I can just choose. Oh, I see. No, no, it is kind of trivial. So we take the case of, or you take z as your lattice. This makes sense, right? You have any two values are going to be different. Yes, no, never mind. That is trivial. Let's look at the definition now. So I want to say, what does the backslash mean in math? I want to say we did this earlier. This just means that it's not in the set. If I'm not mistaken, I could be wrong. Okay, yeah, we're gonna use the so it's some element. So I want to let's look at this definition more close. This is saying the minimum value minimum value in L not equal to 0, the norm of the minimum value. Or that's the minimum distance. don't. That's not. It's not very trivial. I don't know. It's not trivial. That is not trivial. It's not trivial at all. So once again, I want to see how chat will guide me through this, and then things that I don't understand, we'll fill in the blanks. Yeah, things that I don't understand, we'll just fill in the blanks later on. Let's see how chat explains it. I'm kind of curious. Oh, that's pretty easy. Oh, never mind. I'm being retarded. I'm being dumb. So okay. So that was I was close. This is more the. It just means the norm is we know norm is length or magnitude. So now we can just accurately say. Okay, this makes sense. Now that makes sense. So it's just saying that this value we see is min v spans L non-zero. This means the length of the smallest vector in L where L is not zero. Cool. So you exclude the zero vector and you find the smallest vector, and then the alternative definition is saying the smallest vector the alternate definition is saying the smallest vector is the smallest distance. Oh, we'll use length. That's more accurate. Is the smallest length of x minus y. And we can recall that will never equal to zero because that makes sense. That makes sense. I think that makes sense. Yeah, that makes sense. That makes sense. Let's keep going. Central result of Minkowski relates this. Oh my gosh. Is this important? Is that important? Fuck. That was hard. This. No. Okay. It's not bad, but I'm gonna skip this because this is just a whole different level. Minkowski. What's proof? We don't give a fuck about the proof. It's saying the smallest vector. Yeah, so for this one, we're gonna go ahead and look it up instead. It's called Minkowski's theorem for lattices. Let's just look at what this is. Sure, Minkowski's theorem in 2D. Okay, let's look at this. And let's read this. Let K be a convex set in a plane which is essentially symmetric. So yeah, so this means that. So I guess yeah, this does apply to lattices with respect to the origin O. Suppose K is greater than 4. We're just gonna watch this. I don't want to take notes. Yeah, because essentially it's symmetric. Oh. Oh, that's so cool. Hmm. Yeah. I kind of lost towards the end there, but that does make a little bit of sense. So let's go back to chat and let's recap. Okay, let's recap this. Okay. Okay, so I understood this part. What is it saying? So what is the theorem? Ah, I see. A reduction on a lattice. My guess is it behaves like a reduction. Oh, it's not. Yeah, we need to do LLL. Okay, dope. Okay, we're gonna go ahead and look. Let's go ahead and write some stuff down. I'm gonna write this theorem down because this one's more easy to understand than this. This because this is the terminology is kind of all over the place, but this one makes a lot more sense. This is the terminology here. Let me just show you guys. Although no, actually, this is not. No, I mean this is a better definition. It's easier to understand. I think when I get more advanced and I get more into it, I can think about it either way. But for now, we'll write it down like this. Okay, so the theorem. So the theorem is um, cool. Okay, so this one actually makes a little bit more sense now that I watched the video. Okay, so this to summarize it, so this to summarize what they're talking about in this textbook, which we'll skip the proof. We don't. Oh, this is a proof. Yeah, we don't really care about the proof. I honestly don't really care about the proof. We just care about the theorem. So the theorem is. So first of all, we need to talk about volume again. So volume, we just talked about volume. Volume is equal to is equal to the determinant of the lattice, or the right equals depth. So it's pretty interesting. So essentially, I think what it's just trying to say is, let's try to, I guess, draw this out. So let's say I have a 2D lattice. Yeah, I think it always helps to draw these kinds of problems out because they're so hard to work out. You have to kind of draw out what's actually happening. So I'm just going to draw my lattice here. We'll do a checkerboard lattice. Okay, so here's my checkerboard lattice. Let's just see here this. Okay. So this lattice is a subset of Rn. And let's mark some points of C. And let's say C is a convex set within Rn, centrally symmetric, and its volume has to be greater than 2 times the determinant. So if vol C is greater than so let's first calculate what is det L. Oh, we need to figure out the spanning vectors or the basis vectors. So the basis vectors for this lattice, well, we're in 2D. You know what? Let's make it easier. Let's say every point in R2. We'll use every single point, every integer in R2. So this is a z-squared lattice. So the basis vectors, as we know, should be pretty easy. Going to be just 1, 0, and 0, 1. These are examples of vectors that span the lattice, right? So you can calculate the determinant of this as just 1. So vol C has to be greater than 2, right? Because 2 times det L, that L is 1. So if vol C has to be greater than 2, that means the determinant of C has to be greater than 2 as well. So let's now construct C. And now, let's say, let's create a 2 by 2 matrix with determinant, let's say 3. So let's say we have 1, 3, no, let's make it easy. 1, 0, comma, 0, 6. No, I should do 0, 3. That's the easiest example. All right, determinant is 3. Okay, so let's see. C is a convex set. I think it's convex. If our matrix is 1, 0, 0, 3. Let's choose an x value. Let's choose 1, 0, see how that maps. We get 1, 0, maps, so that maps to 1, 0. And let's map 1, 1, 3. Okay. I don't know. I gotta look at this proof more. I don't want to waste you guys' time. I don't want to waste my time either going through this, because this is going to be a lot of, I guess, proof. But for now, I'll just take their word for it. Let's go back to chat, try to understand this again. Maybe you could think about this recursively too. I have to look. I'm going to start this, and we'll say come back to that. Okay, so that's it for lecture 1. So let's go ahead and recap what we learned in lecture 1. Sure, let's recap what we learned. let's first read. So we see we took how many pages of notes? We took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pages of notes in lecture one. That's quite a lot, but these are good notes. Let's start at the beginning. So first of all, we talked about what is a lattice. We talked about also how to find if a set is considered a lattice. And so to recap, a lattice is two things. A lattice exists under two possible conditions. Sorry, my pen was acting up. So two possible conditions. One, the set must be a subgroup of Rn. So you take all rational numbers, it has to be a subgroup of Rn, as well as it has to satisfy the property of being discrete. If it satisfies both properties, you can say that that set is considered a lattice. So what does this mean? A lattice is a subgroup if and only if it contains the zero vector, so the all zero vector. This is common in linear algebra to this is expand equivalent to like finding like the basis. It always has to include the zero vector, and it also has to include. It also has to contain the property such that x and y in the lattice, that x plus y, two arbitrary elements where x not equal to y, should add up to another element also in the span of the lattice, as well as the other property that if x is in the lattice, if some point is in the lattice, its additive inverse is also in that lattice too. And then it has to be discrete as well. So this is kind of hard. I think this one. The way I think about this is that there's a constant distance between each point. So between each point on the lattice, whatever space you're working in, there has to be a discrete distance between each point. Yeah, cool. So we talked about that, and for like being a discrete, or if you can think about it as like a neighborhood, which makes sense too, right? You have a lattice, you should have at each point should be a little neighborhood around that point where there are no values in that lattice. So we have some examples of lattices. So we have the set of all zeros. It is a lattice because 0 that holds, and then 0 minus 0, so still 0, also holds the subgroup rule, and then discrete, the distance is always 0. So this is the singleton set of all zeros, and Rn is considered a lattice. Then we have we have the set of all integers. Once again, this is also a lattice because this is the set of all integers. The distance between each point is only 1. Right, the distance between any two arbitrary points that are consecutive integers is always 1. So it is discrete. And then number 2, we can talk about the additive properties. You can choose any two arbitrary elements in the set of all integers. You add them together, you will get an integer. This also works for z of n as well. You can apply this to the n case, as well as for any linear transformation applied to a lattice. You will get back a lattice. So some examples that are not lattices, I want to talk about the set of 2 times, or the set of 2 times z plus 1 is not an example. And the easiest way to disprove this is just choose 2 arbitrary elements in z. So you would choose, so like the set, so 2z plus 1 represents the set of all odd numbers in Rn, right? Every value of z will map to an odd number. So 0 will map to 1, 1 will map to 3, and so on and so forth. So the easiest way to disprove this is just choose 2 odd elements, 1 and 3. Together you get a 4, which is not in the set of odd numbers. And another good kind of example would be the set of rational numbers. This is not. It passes the set of subgroup tests, but it does not pass a discrete test, as between any 2 rational numbers you will have, or between 2 rational numbers that are close to each other, however you define it, there'll always be another rational number in between, no matter how small you get. So therefore, the distance is not the same. Therefore, it is not a lattice. Cool. We're talking about rank. We can assume full rank of the lattice every time, and we can also treat lattices from rational and integers as integer lattices to encompass both. And also we can then talk about rationality, how rationality is key because that's how algorithms are implemented. And next we talked about lattice spaces. We talked about how to express a lattice finitely using a lattice basis, which is essentially just a linear combination of, or sorry, this is a combination of linearly independent vectors whose integers combinations represent a lattice. So the formal definition was, sorry, I have the formal definition right here. Oh yeah, it's pretty easy. So you have a set of basis vectors, you times each one by some element z, some is some integer. You add them together and you form a lattice. So the cool thing is, there's so important facts to note. Linear independence does not guarantee a basis. That's really important. You cannot have, so a set that is linearly independent will not always give you a lattice. And a great example of this would be the set of 1, 0, 0 pi. Take this as a matrix. This is not a discrete system because of pi. We talked about how a lattice will always have a basis, and the important thing to note is that a lattice basis is not unique. Meaning you can have two basis vectors. You can have one set of basis vectors that can create two different lattices. Or I'm sorry, two different lattices can have the same basis vector. So it is not a bijection in that sense. And we talked about union modulated matrices, which are matrices with determinant 1 or -1. This is essentially just means that there's a inverse that exists, and that is always an integer, whereas it's an integer matrix with the following. Cool. And we talked about how you can actually find if two bases represent the same lattice by checking to see if there is a common union modulated matrix. So because a union modulated matrix preserves the lattice to a change in basis, you will be able to find this, and this is a corollary 2.6. The basis of Zn are exactly union modulated matrices. U spans Zn times n, so the Cartesian product. So yeah, and then I have an example here where you take Z2, and then you form a union modulated matrix in Z2. I said 1, 1, 1, 0. This is union modulated matrix, right? The determinant is equal to 1. Or sorry, -1, which is still 1. And then yeah, you take any elements. So then now you can take any element in Z2. I chose the element 7, 5, but it doesn't matter because the whole point is you have an invertible matrix that is also unimodular, so it'll always be in the span. We talked about fundamental regions. Fundamental regions are also really important because all lattices are periodic, so we're able to find. This is a way to, I guess, compute its. Well, not compute, but I guess a way to just consider its periodic elements. So fundamental region of lattices, we talked about the definition. Right, sorry. So this is kind of a hard definition to understand. So a fundamental region is right here. Set F in the subset or equal to all real numbers is the fundamental region of a lattice if it translates x plus f. So you take some arbitrary element in the lattice, you add the fundamental region, and then you check to see if x plus y or y is. So this one, this makes sense now. I like to look at it again. So a fundamental region exists if you can take an arbitrary element in a lattice, if you add an element that is already in the fundamental region. If you add those two, if your result is also in that fundamental region, you can say that F is in the region of the lattice L. And the great example of this is you consider the lattice of all integers. Let's just say fundamental. Let's say you can consider all fundamental, all that. The two regions here that are fundamental are 0, 1 exclusive and -1/2 to 1/2 exclusive. And this part makes sense because you have to span one, because yeah, the fundamental region has to span, the distance has to be the same distance as you would find in the lattice. The only difference is that it's just fundamental if you're able to, I guess, form that tiling on that lattice. This is kind of hard to understand at first. someone take some more time to understand it as well. And let it be known too, a lattice spaces will always produce a fundamental region. And we talked about using that to talk about a parallelepiped or fundamental parallelepiped, which we saw, which is a figure of like a 3D figure of parallelograms, 6 parallelograms, or 6 faces of parallelograms on the shape, or on like a, I don't know what to call it. I guess on a figure, it's a 3D figure. Um, we talked about parallelepiped, which is just equal to the basis vectors. So yeah, you find the parallelepiped of a lattice by taking its basis vectors, multiplying it by the fundamental region of that lattice. So it's a pretty cool definition. PB equals B times Zn, where n is whatever region your lattice is in, or whatever. Yeah, which is pretty cool. Yeah, you're able to. You also define it, or B times, and this fundamental region, you can define it as -1/2 to 1/2 or 0 to 1. But the first one is preferred. And our last two topics we talked about a fundamental region theorem. B times, or if you have a lattice space B and you have a fundamental region F, B times F is also a fundamental region of the lattice. So yeah, it's a cool way to, I guess, check for PB. It's not really anything too important. We talked about, yeah, so all fundamental regions have the same volume, and we talked about volume is equal to the volume of a lattice is equal to the determinant of that lattice. It's pretty interesting. There's a cool theory for this too. So determinant of a lattice equals volume L, but if volume L is the determinants, if volume L, you can say det L equals to det B, where B is any basis for the lattice. So yeah, it's pretty interesting. It's pretty interesting stuff. And lastly, we talked about minimum distance. We just talked about this right now. So to recap, Euclidean norm, we know how to find. It's just the magnitude of some vector. And yeah, it's because assuming L is because L is discrete, it'll always have a minimum length under some norm. We're going to use the Euclidean norm. There's always some norm that'll have it. Minimum distance of L, we found the length of the smallest vector, not including the zero vector. You can also write this down as the length of the smallest x minus y, where x and y are points on that lattice, or distinct points on the lattice. Then we ended the talk with Minkowski's theorem, which just goes over. This is I don't really understand this too much. This one's kind of tricky. What I got from the video is just means you take a lattice, and you take a lattice L in some space Rn. You take a convex set, which is equal to 2 times the determinant, or has the volume 2 times, or the determinant of that set should have a volume 2 times the determinant of the lattice. And this just proves that the set C, or that convex set, will have at least one point that is non-zero that's on that lattice. I don't really know what this really entails, but it's important for the shortest vector problem. So it's important to know. I'll probably go back to that later. Cool. So that's lecture 1. Pretty much summarized. A lot of cool fundamental things to talk about there. Let's go ahead and start on lecture 2 now. Let's get some music going again. All right. Lecture 2 PDF. What are you going to learn? SVP. Oh wow, so this is going to cover quite a bit. Okay, we have a lot of material to cover here. Graham Schmidt. My old teacher he used to call us Graham shit because he thought it was super inefficient. Yeah, he hated Graham Schmidt. I remember that. I'll never forget that. He did not like using it at all. Yeah, just a way to find an orthogonal matrix. Alright, let's start off with the shortest of the problem. So last I'm going to find a minimum distance of a lattice that is upper bounded by. Sure, that's some formula. I see. Symmetric computation. Can we compute its minimum distance? Okay, cool. So let's go ahead and define. Let's go ahead and define the shortest vector problem. Cool. Okay. Let's start off with the SCP. This is gonna be a pretty hard lecture, so that we're probably gonna only get through probably 1.1, 1.2, 1.3. All right, let's start out with 1.1. We have a new definition. Okay, first one. Hmm. So the first one just says, given a lattice basis B and a real D over than zero, distinguish the case between hmm. There's a little footnote here. It says two. Oh, it says D squared. Oh no, never mind. Not D squared. So I guess in human words is all this. All it just says is just two. Yeah, this means compare the minimum value of lattice with D, whereas two says. So I'm looking at this. Of course, the obvious answer is if you calculate two, you can calculate one by default. Oh, I think. Oh, I get it. Never mind. I get what this is trying to, I guess, say. It's just trying to say there are three different ways you can approach trying to find the exact SVP. So three is just saying find length find length of vector equal to min value of lattice. That's pretty cool. Okay, that kind of makes sense. I kind of understand this. It's just trying to show us that there are three ways you can approach. You can either just get the full-on calculate, you can search, or you can just, I guess, keep making small decisions. Now let's write down like remarks. Decision. And the same is true in the other case. Not if such as exceed in polynomial time. Cool. So the order is polynomial. Also, get interested in what are approximate versions of SP. Interesting. I'm not really too familiar with this. Go ahead and write it down. That symbol is hard to draw, by the way. That is a hard symbol to draw. I'm just gonna say R. I'm not drawing this little symbol. It's not easy. It's not just not trivial. So here we're just approximating. So let's talk decision. I guess the decision is very similar to the binary search. I don't see how this is too much of an improvement. I don't say this is too much of an improvement. That's cool. They only mention R in here. R only in this term. It's kind of hard to, I guess, understand. We'll just go on. I just end up looking this up. So this is not very trivial at all. So it says here. So saying gap SV of R prime. Dude, this is not trivial at all. Well, I guess now this one makes sense. It's saying if R is bigger, then so a bigger R. Oh, it's not just. This is hard. This makes no sense actually. Like I don't even know where to start. It's easy to check though. Oh yeah, this one. This makes sense. When it says yeah, but what does it say? What is there? Cool. Yeah, this is not. Okay, so this is we're gonna stop here for today. Let's actually get. I want to get an example. I'm gonna go on YouTube. Let's find. Look at procrastination. Okay, there's not many, dude. There's like no videos on this stuff. This looks. What is ants? I keep hearing that. Oh, this is a great video. Oh, this is a great video. This is a great video. We're gonna start this for tomorrow. No wait. Save. All right. It's not there. It's not there for tomorrow. Well, I want to watch the whole thing actually, because this all looks like really good stuff. Yeah, this is really good. Okay. Wow, I'm excited. That's gonna be great. We'll spend actually tomorrow and just look at that video first, and then maybe we'll do a little bit more here. But I think I'll spend like a couple of days on this shortest bit because this is the meat of, I guess, lattice-based cryptography is the shortest vector problem. That's what I want to implement too. So I'm gonna spend a good amount of time making sure I know the fundamentals. Um, it's cool stuff. I mean, we're chugging along. I mean, it's slow, but it's part of the process. Yeah, I'll see everybody tomorrow. It's 11:51, so it boys me back here pretty soon, anyways. For day number 4, we'll the theorem and try to get some concrete examples and try to understand it more. Hopefully, they'll get into some C code maybe next week. Yeah, maybe in maybe, or it could be in a couple weeks, could be a couple days. I have no idea. We'll see. But for now, that'll be it. Take care.